talks in the afternoon. And so we will start today with the second lecture by Vivian on cosmology,
Yes.
and this will be a Blackboard talk. So please take it away.
Very good. Thank you very much for coming back and not being afraid of the first lecture. So I try to summarize what we have seen so far. I have to use this thing. So what we've seen so far is that the cosmic neutrino background was formed at a temperature of order 1 MeV when the weak interaction dropped below the Hubble rate. At that time, the neutrinos that have been in thermal contact and acquired a Fermi-Dirac distribution keep its Fermi-Dirac distribution, although it's not anymore in thermal equilibrium. There are no known processes that alter that distribution. So we talk about a frozen distribution. And I had pointed out that because they froze out in a regime where they are relativistic, their temperature at that time is much larger than any reasonable mass to the neutrino. It means that they keep this distribution with a P. There is not explicitly a mass appearing in the distribution. Then we had computed using the entropy density conservation, specific entropy conservation. We had computed the temperature, which is the only parameter defining our neutrino background. And we had seen that because of electron-positron annihilation, the temperature of the neutrino is a little lower than that of the temperature of the photon, which is usually taken as being the background. And we had derived this famous 411 to the 1/3 refractor. Then we had just counted stuff. We had counted how many neutrinos we had. We had counted their energy density, which is what matters the most in cosmology, how much they weigh within Einstein equations, basically. We had seen that there's about 110, 12, 30% neutrinos per flavor times this number of flavor and effective, which is equal to 3, roughly, in the standard cosmological model, plus some correction from the fact that electron-positron annihilation arrives very close to the neutrino decoupling. Then we had defined, so the energy density in terms of the photon density. And what I had not had time to do is properly define the transition from when the neutrinos go from relativistic to non-relativistic. Of course, in practice, all you do is always compute an integral of that form at all time, with density being defined simply as the same integral as here, but with the average energy carried by the fluid. So the same three factors, except you replace this guy by this guy to get the energy density. So in principle, you just follow explicitly this distribution. But roughly speaking, we can differentiate two regimes. The regime where the temperature is much greater than the mass, and the regime in the opposite, explicitly, the opposite regime where the mass is much greater than the temperature. And the transition can be estimated by requiring the mass to be of the order of the average momentum. You could do it also by requiring that the equation of state, which is the ratio of pressure and density, is around 1/3. These are all various approximations that give roughly the same number. And when you compute the average momentum, you're going to find that it's 3 times the temperature. And so we get this mass over 3 times the neutrino temperature, which when you plug numbers, you find this 2,000 times the mass of individual species divided by 1 electron. So that defines the redshift at which neutrinos go from diluting as a to the -4 to a to the -3. Okay, and again, in details, there is a transition here. It's not exactly a to the -3, a to the -4. You have to follow the. Okay, and I had made a mistake that was pointed out. Thank you. Very good to follow. That when I define the pressure, what I had done is to take the average of E squared, which is not what the pressure is. Pressure is the average of P squared divided by 3E. And to see that three-factor, you have to go back to kinetic theory and the fact that pressure in kinetic theory is analogous to the momentum flux. The momentum flux along one direction is the product of the momentum times the velocity along that direction. And the velocity itself from Hamiltonian mechanics is the ratio of the momentum over energy. This is true for a free particle. So that gives us a P square over E, but because this is along one direction, pressure is defined according to 3 directions in space, we have that statistical isotropy tells us that Px is P divided, the norm of the momentum divided by 3. So we got this P squared over 3e in this as a prefactor. Sorry for that mistake. And then when we see that, we understand that E, which is square root of m squared plus P squared, when P drops, you're going to get this 1 over m suppression, which tells you why. When the mass becomes big in front of the temperature, you get that the pressure becomes negligible. Okay? This is the summary of the first lecture, and we're going to keep this up. And the goal of next lecture, I can maybe write that down, is to describe what we have seen with the exercise notebook that hopefully you can keep, and one day if you can reuse, try to look at what the effect of neutrinos on the observables are more carefully. You can understand better after this lecture. And the goal is to understand how to constrain the neutrino mass, constraints to the neutrino mass. And the next lecture will be about constraining the number of effective species, of course, not coupled to the weak interaction, because we had said that extremely well measured just from Z boson invisible decay. So we're going to talk about the number of basically sterile neutrinos. So constraints to the neutrino mass and from cosmology. And what we will see is that there are basically two effects that we care about. We care about the fact that massive neutrinos contribute to energy density like matter, so proportional to 8 to the minus 3. So this means that it's going to alter h of z. I'm mixing up redshift, scale factors. Is that clear for everybody? I'm sorry for being a little sloppy, but the definition is basically that the scale factor is connected to the redshift by just an inverse slope. Okay? So sorry if as I speak, sometimes I mix up scale factor and redshift. But so this means that it's going to alter the Hubble rate when you transition from a massless universe, the universe where neutrinos are, or at early time when neutrinos behave as if they were massless, basically, to when the effect of the mass becomes important. Okay, and I just rewrite here the definition of the Hubble rate that comes about from Einstein's equation. Okay. And the second problem, the second thing is massive neutrino do not cluster on small scale, on scales smaller than the so-called free streaming length, because they are free streaming. So they mean they can escape gravitational potential wells for the same, because their velocity is of order average momentum divided by the mass, okay, which we have just computed here. If you put the right C prefactors, you'll see that you get the right units, basically. So this means, now I'm going to write it slightly differently. Something that looks like this. 150, let's see, let me remind that so we have some space, sorry. We're going to try and derive these things a little bit better later. So this average momentum divided by the mass is of order 150 times 1 plus z, 1 eV over the mass, kilometer per second. And the difference should be factors of C and D. Okay? So because they are free streaming, it means that on scale that are going to be smaller than basically the velocity times the time that has spent since, basically, I don't want to say the Big Bang, but since reheating, typically when the particles are produced, that represents the distance scale, and that distance scale is the distance over which neutrinos are going to travel. And so there's going to be a difference between scales that are below that free streaming scale and scales that are above that free streaming scale. And that means that the neutrinos alter, that means they alter the clustering of matter. So delta rho matter, which we will define better. Okay? So there are two effects It's important to understand that they are connected but different in the sense that we have probes that simply probes background properties. We don't see at all this effect of the clustering or the non-clustering of neutrinos on small scales. And then we have probes that, on the other hand, really target these effects. And the idea is that this is supposed to be a little bit more a smoking gun signatures of neutrinos, even that can be debated. While this, because you see you're summing up over every species in the universe, in for instance, dark energy is going to contribute here as well. If these have exotic properties, you might alterate the bounds that you derive. Okay. So let's see now how we can use cosmic probes to get constraints from these effects. So I'm going to try to keep this up. Any questions on this part first? Yes. So,
if they were massless, would they?
Yeah, if they were massless, yeah, then basically their free streaming length is the size of the Hubble horizon, of today, So you'll see that in the equation, what happens is massless neutrinos at late time. So to sketch what's going to be the problem is that because they dilute like matter, they matter in H. And there's going to be a competition between H and delta, which from the Poisson equation, basically, we're going to see that. And what's happening is that if the radiation at late time, they don't contribute to H. Because they don't contribute to H, they don't, in fact, even though you could think, oh, the free streaming length is huge, in cluster, why doesn't it just suppress the matter power spectrum? It's just because they don't contribute to H at late time, because they dilute it so fast. While massive neutrinos have had this property of free streaming, but eventually the background contribution starts to dilute like matter, so there's a weight in the equation.
Okay.
And
one more thing, I think it's just rho and this H square in the first equation.
Wait, then Lisa?
H square is equal to rho by 3 ampere.
Yes, of course. H square is.
We can get you a letter.
I know.
A letter.
So I used to have a professor who would give chocolates for people who found mistakes on the blackboard. We like that. So I did not get chocolate. Yeah, right. Cube. Yeah, I did right cube. Okay. That's the two. Okay, that's the two. Okay. Okay, so the main probes that we have in cosmology can briefly say there are to probe neutrinos, I should say there are three main probes that you might have heard of or will hear. These are the main probes are the cosmic microwave background, okay, and the temperature and polarization anisotropies in particular. So this is a black body radiation at the temperature that we have already defined, 2.7255 plus or minus, sorry, 0.001 Kelvin, okay? And the statistical properties of that 0.001 on the sky is the thing that carries cosmological information. Well, I should say that the black body temperature also carries some cosmological information on the black body distribution in general, and in particular looking for deviation from the black body radiation spectrum can carry cosmological information, but what we are mostly using nowadays, because we don't have the sensitivity to those deviations, is the anisotropies. So just to be very clear, what this means is that in each direction of the sky, if we were to measure the spectrum of the sun, the count number of photons as a function of frequency, we would see that in each direction of the sky that we do this exercise, they always follow a black body temperature, sorry, black body distribution, except that the temperature that defines the black body is very slightly different, okay, by this amount. Sometimes a little hotter, sometimes a little colder. Then we have galaxy surveys. And in particular, the baryonic acoustic oscillation that we've already seen in this notebook. Sorry, I'm trying, and I'm blocked by these things. I want to not write about this. So this is what the acronym that we write as BAO. And I want to stress that the BAO is often seen as this thing we see in the galaxies, but it's the same phenomena that we see in the CMB. It's the same. The only difference is the tracer that you're using. Here you're using photons to see the baryonic acoustic oscillations, right? Here you're using galaxies which are connected to the matter field, which is connected to the baryons and the cold dark matter. And the last probe that's very important, but I won't go into detail of it during this lecture, is Lyman alpha. And the reason is basically, I'm going to cite it because this is historically one way to get very strong bounds. But the idea is just because you want to probe the suppression of the matter power spectrum on small scales, you just want probe of the very small scales. And Lyman alpha is one of the probe, Lyman alpha forest, and the 2-point correlation function in the Lyman alpha forest is a probe of the very small scale. So this is the measures very small. So it's the Lyman alpha forest power spectrum. Okay, something we were going to define. The Fourier transform of the 2-point correlation function. Lyman alpha forest power spectrum for the very small scale. So roughly speaking, and we will try to reach that point drawing, large scales are probed by the CMB, intermediate scales are probed by galaxy surveys and the BAO, and on very small scales, we get Lyman alpha forest. Okay. Okay. So first, I wanted to derive the first you could ask, let's derive a very robust constraint to the neutrino mass. Let's derive a very robust constraint. Something that even for people who are not doing cosmology, you can think of as, yeah, this is clearly, it should be a bound that is very important, and that is that the neutrinos are are massless at the time at which the CMB forms. Because we know, because the energy density of the stuff in the universe was dominated by radiation, okay, around the time of CMB forms. Actually, if we do a drawing, let's do a quick drawing of redshift in the various epochs. So so we have that. So and let's do the densities. So we have radiation. Sorry, so this redshift goes in that direction. Then we have matter. Okay. So we have a time that's important that's called matter radiation equality. And we have another time that's very important, that's very close, and it's called recombination, the time at which the CMB forms. And when we plug in the numbers, we have that matter radiation equality is around 3500, and the recombination redshift is around 1100. And if we don't want to completely mess up the CMB, we can already just ask that our neutrinos remains radiation, like radiation, at recombination. And this, you see, that gives us just orders of magnitude already of the bound that we're going to get. All we have to do is recombination something that you've never heard about, that I should quickly define, though. So just for people who would not want to answer that question, let me just say that this is the era at which neutral hydrogen forms, protons and electrons. Before that, we have ions of hydrogen ions, of protons and electrons in interaction. After that, we have neutral hydrogen, and the photons can propagate. Okay, and if we can quickly derive using just this formula, if you plug in that the non-relativistic transition has to be basically below 1100. Okay, you are going to get. You just put. That you're going to get inverting this relation, you're going to get that the mass has to be below 1100 divided by 2000 on EV. So that already gives you a mass of order 0.5 EV. Okay, so lower or for individual neutrinos in this exercise, not the sum, each individual neutrinos, but so it means that the bound on the sum of neutrino mass just from this very quick exercise is somewhere like 1.5 EV. And I just recall you that, let me remind you that that's about the level that we have with experiments nowadays in lab from just 2025. And all I did is just asking that my neutrinos don't mess up, are not massive, don't act like dark matter as opposed to radiation at the CMB, which is a very simple exercise. Okay, tells you about roughly how strong the cosmology can be from a very. This is extremely robust. There is no strong degeneracies here happening. And you see that basically, because there is this redshift dependence, if I want to get to smaller and smaller constraints, I'm going to have to probe, I'm going to try to probe with lower redshift probes, basically. Do I see that transition from radiation to massless, to massive, to matter, And so if I manage to get probes of lower redshift that are sensitive to the transition, I might be able to get probes of to get much stronger constraints, which is exactly what's going to happen with galaxy surveys. So we can write that being sensitive to neutrino mass, being sensitive to 1 plus ZNR, means what you're going to want is to have a probe that redshift, basically. So basically, what you're going to want to find is probes that are sensitive. If you want to push down the mass of the neutrinos, the constraint to the mass of the neutrinos, you're going to want to try and probe when that transition happens. You'd like to see that the neutrinos were massless before and then become massive. Okay? And the best term that we have is the best probe that we have that is, again, quite robust is this baryonic acoustic oscillation. So what is the baryonic acoustic oscillation? And this, by the way, in galaxy surveys, at this probe redshift of order 0.1 to, let's say, 2 EV, sorry, 2, yeah, 0.1. And so what is this baryonic acoustic oscillation? So I already mentioned it with words on Monday. What it is the remnant of a sound wave that has propagated prior to recombination. So just to be very clear again, before recombination, what we have, we have, these charged particles, and the mean free path of photons is extremely small. They move, but it's very, very small. Okay? And at recombination, the escape. And in this tightly coupled plasma, a sound wave has propagated. And that's what we see as the baryonic acoustic oscillation. So because it's a sound wave, we can just compute that the distance over which it has traveled, which we call the sound horizon, is equal to the integral of the sound speed over conformal time. In cosmology, we use conformal time. I remind you that conformal time is, I think I called it tau before. Sorry, I'm going to try to keep the notation. Is equal to dt over the scale factor. Okay? And if you use the fact that dA over dt 1 over A, so this is what I call A dot over A is equal to H, and that A is equal to 1 over 1 plus Z, you can rewrite that simply as the integral of the sound speed over dz H of Z. Okay? And that integral runs from reheating, basically the end of inflation, reheating, to recombination at the time at which we are freezing the plasma. Again, I'm going to give that image again. What you need to have in mind is exactly like what happens in Lake Michigan when you freeze suddenly the lake and the waves freeze in the sky when you go from a plasma to a gas. Well, in the case of the Lake Michigan, is liquid to solid. Here is plasma to a gas. Okay. So ZRE, Z-rec. We are lucky because so this integral, so maybe I should write, let me add. The sound speed is, because it's a relativistic fluid, so the sound speed of the fluid here, we are talking of the fluid made of tightly coupled photons of the CME and electrons and baryons, okay, electrons and protons. But because the photons matter so much, basically. It's a relativistic fluid, and the sound speed of a relativistic fluid is simply the speed of light over square root of 3. There are corrections to that because of the fact that baryons are not relativistic, close to matter-rich inequality in particular. They start to matter more and more. There is a correction, but to a first approximation, it's basically the sound speed divided by square root of 3. Basically, same sort of, of argument as what is written here in terms of where the square root of 3 comes from. It's very similar, saying it's p square over 3. So we can just do this. So in principle, you're going to say, so what is h of z? Let's rewrite it explicitly. H of z is h naught times the various. So we are at early time. So what matter at early time is radiation and matter. Okay. And we are going to want to integrate that thing from some hypothetical reheating redshift to recombination. Obviously, we don't know this redshift. Fortunately for us, this thing is dominated by the lower bound of the integral. So it's actually very simple to do that integral. You could put 0 here, you get the same results. Fortunately for us. I mean, I guess fortunately or unfortunately, because you could get dependence on the reheating. So this is roughly 0 here. We don't care. Sorry, should write infinity in terms of redshifts. Here again, I'm making a mistake. So this is roughly infinity. To recombination. And recombination, we define, I said 1100, you can get slightly better, you can go 1080. I should say that if I don't want to be too sloppy, I should say that for baryons, the recombination, if you wish, the redshift that you have to put here is very slightly different. Because photons escaped at 1080, at 1100, but there are many, many, many more photons than there are baryons. The so-called photon to baryon ratio, eta, is basically number density. This photon to baryon ratio is order 10 to the minus 9. It means that, what that means is that from the point of view of a photon, there are very few baryons, so it's easy to escape. But from the point of view of a baryons, there's lots and lots and lots of photons around. So it's hard to escape. So the rates always involve functions of the number density times the cross section. The cross section is basically the Thomson cross section here. But the number density that I put is not going to be the same. And comparing this to H, when you solve correctly the Boltzmann equation, you realize that baryons actually have a slightly different decoupling. We call that the drag redshift because it's the end at which baryons that were dragged by the photons, they release from that drag. And that's like 10, I want to say 1060, right? Basically the same, okay? Slightly different. So that's sound speed, that's sound horizon. You could do the computation, just put in the value of H naught, etc., and you'll get that the sound horizon, let me try to rewrite this so I can put it here, sorry. And I'm going to prove that CS is C over square root of 3. This is equal to, if you do it with C over square root of 3, you're going to find 160 megaparsec. If you do it with the correct correction that I was saying, because baryons start changing the pressure, the sound speed, you get 150 megaparsecs. Okay, so that's 150 megaparsec is that scale that we see in the sky, in galaxies, in the CMB. Very simple computation. To see why this scale appears, strictly speaking, you have to solve and we will sketch down this in a second. You have to solve the perturbed Boltzmann equations, and you'll find an equation, you'll find a wave equation with a sound speed that's given by this. So I will write it down finally. Okay. So now what we actually observe is not directly that. What we observe is angles in the sky. And since these angles are small, I'm just going to write that it's the physical scale divided by the angular diameter distance to some redshift. So the redshift here can be either the CMB redshift, if we observe the CMB, or the galaxies. Okay? and the sound horizon is the same, basically, 150 megaparsec. Okay? So this is fixed. I'm going to write, for the CMB, it would be Z star. I'm sorry if it's a bit sloppy, but it's either Z star for the CMB or ZD for the baryons. I'm going to skip this notation very quick. For the galaxies, sorry, it's slightly different, but you understand that basically this is 150 megaparsecs. And the angular diameter distance is connected to, sorry, I'm still sick, to the co-moving distance that we had derived before.
You want some water or?
No, I think I might have to use tissue later. I'm sorry. Simply, we have to multiply the co-moving distance, which was given by the integral of d tau. And we just derive that the integral of d tau, sorry, I can do this on the board, you can't, but I do it. This thing, time, the scale factor, because we want to scale the physical distance with the scale factor. So it's 1 over 1 plus z, if I'm writing it. This is called the angular diameter distance in cosmology. Okay? And here now you can see, and sorry, and this integral runs now. So the diagram that you want to do is, let's take two galaxies. I'm observing from Earth here. This sound horizon is the typical distance between galaxies. Of course, that's the sketch. The angular diameter distance is this. So here, the angular diameter distance now runs from redshift 0 to the survey. So I should write prime here, to whatever redshift I want. And what I'm looking at is the angle. Okay, that's the angle theta. Theta is. So you can see now that my cosmological information, so this is fixed. I know that there is important information because so this integral here in the sound horizon is at early time. So it probes mostly basically radiation. So that's going to be important for n effective. If I play with the amount of neutrinos in the universe, I'm going to change the sound horizon. Okay, I'm going to keep n effective to. I see some red faces here. Is that okay? Or just if I boost this, I might change the h here. Okay, that's it. But in this exercise, I'm going to keep n effective to 3. There's no weird stuff happening. So this is basically fixed. Okay. But now the h of z, in the denominator is what I care about. Okay. This integral runs from 0 to some redshift, and this is what I care about. So this is a number, and this has the cosmology dependent that I'm talking about. And you can see that if I compare the size of the sound horizon at two different redshifts, let's say, Z star, the CMB, over some lower redshift from the galaxy surveys, I'm going to get that this guy is going to cancel out, okay? Because it's basically the same number. So I'm going to get ratios of angular diameter distance. And that's how, from this sort of comparison, this is called the standard ruler, by the way. The name is called standard ruler. An object of intrinsic size, which is, I don't want to say known, because we have to have a model, but which is the same between, that we can use to calibrate. So here I have used the fact that the sound horizon in the CMB and the sound horizon in the galaxies is basically the same to write this ratio, and I get that now I have dependence on cosmology through these ratios of distances. Okay, and roughly speaking, what we can say is that what we are going to do is to compare. Did I write one? Yes. We are going to compare the amount of matter that there was at the time of the CMB to the amount of matter that there was at the time at which I'm doing my galaxy survey. Okay, and I'm trying to make sure that my omega matter that appear. So I'm, below 1,000. Really, this is. Let me write it explicitly. So, if I'm above 1,100, at high redshift, this is this pound that matters. And if I'm below 1100 at low redshift, omega radiation times 1 plus d to the 4 is negligible, and it's now this pound that matters, okay? And the rough idea is that I'm going to be able to compare that omega matter that I derive from the CMB at 1100 is the same that omega, sorry, or different from the one of the BAO. And roughly speaking, we expect that omega matter BAO, and by BAO here I mean galaxy survey, because neutrino becomes massive, has to be slightly bigger than omega matter CMB. Okay? That's the naive expectation that you would get from the fact that you go from a matter dominant, sorry, from a massless neutrino to massive neutrino. And in fact, it's the opposites that we have observed so far. So how do we extract that angle? We do it statistically. We use what's called the two-point correlation function. We don't just take two galaxies and say, oh, that's it, that's their distance. It's a statistical property, the same way I could use you guys to see whether there's a characteristic scale between people, you know. And I would probably find that, you know, you're probably far away from me, you know, you want to hide in the back. There would be a peak distribution far away from the professor. And so to do that, we compute the probability. It's a probability of finding pairs of galaxies separated by a certain distance. So that probability is first, it's within a given volume. So what this is going to be a conditional problem. Given that I sit on a galaxy, what is the probability to find another galaxy at a certain distance r? Okay? There is a random noise. There's a Poisson distribution. I can just throw, you know, basically things are roughly speaking random. But there's a little increase quantified by that correlation function, which we call psi, a little excess of probability that is going to carry the information from that standardized. So strictly speaking, this correlation function psi, this is the excess probability. Is defined as the volume average of the product of the density field at a given position times the density field, so the over density field, where deltas are delta rho, which now depends on position, over rho bar, which is the average and homogeneous contribution, at x plus a distance r. And because of statistical homogeneity and isotropy, doesn't depend on x, and it only depends on the norm of r. My little vector doesn't depend on which direction I'm doing this exercise, it just depends how far I am from my galaxy. Okay, that's called the correlation function. We've computed it, we've measured it, and it looks like this as a function of r. The two-point correlation function, good. At low distances, we have a peak first, because galaxies are found in halos. And then if it was purely random, you'd expect that, basically. As you increase the distance far away, you have less and less galaxies. But in reality, what we found is a bump. And I let you guess what distance this is. It's going to be 150 megaparsecs, but everything is, we don't really measure, as I said, directly the distance. What we measure is some angle. So there is a over h. The free scale is how far things truly are, because we don't know the absolute calibration. Okay. And actually, I think because it's over h, we're going to have it might be like, well, the truth distance is 150, h is of order 67, and it should check, but it must be order 100. The distance is 100 megaparsec divided by h, such that the physical distance becomes this 100. Okay, and that excess probability is smaller. It's 1 to 2%. You're looking at a little, at a certain distance, I have more chance to find galaxies separated by that distance, very small. but it's been observed already back in 2005 by the SDSS collaboration, and now by the DESI collaboration. And the DESI collaboration, in fact, measure what we do now is we're able to measure three. And I think I'm only going to have time to talk about the BAO today, unfortunately, and we'll do the suppression of the matter core spectrum next time. I think it's more realistic. I'm going too fast. And so what they really measure are they measure this angle in three ways. They measure it. It's measured in three ways. It's measured perpendicular to the line of sight. So this is really the drawing that I did. It is measured twice because it's measured, perpendicular this way and perpendicular that way. Okay, vertical and horizontal. So we have theta perpendicular, which is really this RS over dA. And this is twice. Okay? And then we have a little bit more subtle. We have theta parallel along the line of sight. In that case, it's not the sound horizon divided by dA. It's simply given by, I shouldn't really call it theta. They call it theta by abuse of notation, but really what it is the, so it's delta. Let me write explicitly. What they measure is the distance. They want to measure the distance along the line of sight. Okay, it's the integral delta. Is the integral along the line of sight of the sound speed. They're trying to measure that. Of the lights emitted. So of the lights. Yes, like this. So it's the distance along the line of sight, and that distance between two infinitesimal, two bins, Z and Z prime, and they are going to fix that this guy is equal to RS. So this infinitesimal becomes this thing, looking at a small redshift bin, and this is equal to the sound horizon. Okay, it's along the line of sight. I should see that there are, for galaxies separated by a specific delta Z, there is also a peak in the distribution. And because this is small, I don't care about the Z dependence. I put some effective redshift here, if you wish, that represents the beam. Okay, and this, now I define that theta parallel is equal to C delta Z, just by analogy with respect to the theta perpendicular that I defined here. Okay. So what's great about theta parallel is that, strictly speaking, this angle, this measurement is directly probing h of z, as opposed to an integral over h of z. Okay, you're really probing the error rate at that redshift and not the integral over. So you have, in principle, a stronger dependence on cosmology in this. Okay.
So here you need some redshift information.
Yeah, you have everything. So DESI measures the spectroscopically the redshift to tens of millions of galaxies. So DESI, spectroscopic redshift, spectroscopic Z to tens of millions of galaxies. Okay, in redshift 0.1 to 2. Okay. And very good. So I said we see the same pattern also in the CMB. Very good, very good. And what we find now with, maybe I'm going to have some time. What we find now, if we combine, so what we're going to do now is measure this angle, these three angles at low redshift, measure it in the CMB sky. I've already erased it, but at high redshift, and we're going to find correlation between between the neutrino mass and some cosmological parameter. So let me write explicitly before I do this drawing. So let me write explicitly the dependence that we should find. So we have that theta So what is measured is this angle theta. We said it's Rs over the angular diameter distance to some redshift. Very good. So you see that the angular diameter, is that still written somewhere on the board? No, I erased it. I just erased it back. So let me rewrite it. So the angular diameter of distance is the integral dz is 1 plus z, sorry, 1 over 1 plus z divided by h of z. H of z, just to break it down again, is h naught square root of the different species that I have, sum over the different species that I have. Okay. And so if I can extract some of the dependence, so I can put h naught, you see, it's going to be, there's going to be a 1 over h naught here in the dA. Like, this is a constant, okay? There's a 1 over h naught here, so I can, this is going to give me just the product of h naught times rs, okay? Divided by this integral, which we usually write as dz over e for expansion, if you wish, where e is simply the ratio of h of z over h naught, okay? And within this e of z, there is my different components. So you see that the BAO, because it's an integral in the galaxy surface, because it's an integral that runs at low redshift from 0 to 1. So within BAO, I have sensitivity. I can measure the product of h naught and rs, this guy, and I can measure omega m, and I should add that omega lambda in a flat universe is just 1 minus the sum of every component, but the one that dominates. So I can add the radiation, okay? The radiation is 10 to the minus 4. So it's really 1 minus omega n is omega lambda. So what this means is that you only have one really unknown here. You have only omega m as far as the galaxy surveys are concerned. So within lambda CDM, basically what you measure are h naught rs times omega n. Okay? Radiation subdominant at low redshift, and you just get information on that product and omega n. Within the CMB, now the integral runs up to higher redshift. Radiation is not negligible to that redshift. So you get h naught rs, omega m, and omega r. Okay? And by comparing the omega m that you measured from the CMB to that of the BIO, you can get information on what has transitioned from radiation to matter. The rough idea of the problem. And so we can, so neutrino mass are going to have correlations with cosmology. So basically, they're going to increase omega matter in the low redshift universe. So, and you can see that they're going to be correlation with h naught. Because as well, first with omega matter. So first with omega matter, we expect to see something like this, the increased omega matter. Very good. The problem is that, so this is from the CMB. And the problem, as I said, is that the BIO has measured that. So this is around 0.3. And the BIO has measured somewhere around 0.28. So when you combine the CMB and the BAO, you end up having constraints that look like this. Instead of being where you would have liked, basically on the large side, like somewhere here, you would have liked to see something like this, and you get the detection, but what you got is the opposite. There is a little bit of an inconsistency, let's say, but that leads to a tight constraint. And then there's also a correlation with h naught. It's very clear from here, I think. If this guy omega n increases, I can compensate that by decreasing h naught. So you have an anti-correlation in the CMB. And here again, unfortunately, the h naught rs, so rs is fixed for this exercise to 150 megaparsec. So the h naught is basically coming from the BAO. Well, it turns out that it's slightly larger. So it lies on this side, if you wish. So again, leads to a tighter constraint that you expect. So you expect that if neutrinos had become massive, you should see that compared to a universe where neutrinos are massless, H0 is a bit lower. And it turns out that what we observe at low redshift is the complete opposite of the picture that I'm giving you. Everything is at the 2 to 3 sigma level, okay? It's not like yet a big issue. But this means that when you combine, as I said, Planck plus BAO, sorry, plus all the great CME surveys that we have to get the tightest constraint basically to this theta, this angle, if you wish, plus BAO, you get that measure that I told you, which is 0.48. And what is the solution to that? Is that maybe when we did this exercise, well, of course, the solution could be a statistical fluctuation in either the BAO or the CMB that should, this status coming from this measurement of the BAO could be just statistically due to a statistical fluke a little on the wrong side, if you wish. Or there could be a systematic, etc. But it's hard to make systematic really because you see it's a very simple measurement. I mean, all I'm doing in the end is 2 I have a map of galaxies. I've measured the redshift. It's quite clean. There is no complicated physics, and it's very large scale stuff. And all I'm doing is I'm counting the galaxies and I'm comparing, basically with respect to a random distribution, I'm comparing the excess probability. I'm computing the excess probability with respect to a random distribution. And so it's not that easy to find a systematic in that sense. Yes.
So how do we define this is the scale where homogeneity and isotropy would be valid, so that we can apply this metric and do all this kind of calculations. So how do we define that particular scale? Maybe the homogeneity assumption may be big.
In the scale itself, we know that on a very large scale, the properties are such that it's very clearly almost perfectly homogeneous and the CMB being the same temperature as 10 to the minus 4, is a really good proof.
Right.
The transition, we know that on small scale, things are definitely not homogeneous.
Yeah, that's why these two work.
You can look at it, through these large galaxy surveys, try to find the scale of homogeneity. We can look at, when does the motion of stuff look like they are following the Hubble flow as opposed to being influenced by peculiar velocities? There are exercises, there's something called cosmic flows where we try to find the scale of homogeneity. But it's not easy. But roughly speaking, we expect that because of the value of H0, let's see, we can define. We expect that around 100 megaparsec is the naive I should say, because of the value of the sun horizon. This is the type of scales that define homogeneity in isotropy. It's the order of 100 megaparsec and above. But there is no clear, and with this that we've put, it's a simplification, and we don't exactly know when the transition occurs. There are ways to define it, asking when does this density becomes non-linear, for instance, would be a way to try and define things. But yes, I think I'm going to stop here for today. And I just wanted to say that the possible solution to that is to say that here, what I've done is within lambda CD. But what if there is something else? What if lambda is not lambda in particular? Or what if dark matter was not stable over cosmic time? These are the sort of solutions that today people are actually studying. Okay. Thank you.
Thank you, Vivian. Do I see this correctly, that he would prefer negative masses? Yeah. So for both of these,
That we should have is negative.
Also Katrin has a best fit, which is at negative. It's a different measure, but it's kind of a conspiracy here.
We should keep in mind that really, as I try to stress, all we are sensitive to is the energy density, okay? And it's the sum of all the species. So if there was something, and actually the simplest solution, theoretically speaking, again, it's hard to say, it could be a curvature component. If you had a closed universe, you had a negative contribution from omega k here, minus omega k if you wish, 1 base square. And now there are papers looking into this. The problem of curvature is that we wanted to get rid of it because of true inflation. And I think I wrote down the number actually. You would need an omega k of like 10 to the minus 3 or something like this. I forgot why. Yes. And I think it's omega k of order 10 to the minus 3. And typically that would rule out our simplest inflation model. Alternatively, I said dynamical dark energy will have this disasters.
Okay, we have maybe time for one question. All clear? Good. Then, yeah, let's thank Vivian again. And we have a